Sì, adesso lo metto. Eccolo qua. Okay. Good morning, everybody. Today it's the last day of our tutorial, and what we would like to do is actually to move from outside one single node and try to understanding how can we program and how can we run on more than one node. So today this morning I will try to do an introduction to parallel programming, introduction to parallel programming intended here as parallel programming using message passing paradigm. Okay, and the idea is actually to give you a very broad overview to know how an MPI program can be written, the basic element of an MPI program, and then in the afternoon or maybe also after the coffee break, I have a couple of, I have a small example you can play with, just understand what you can do, and then in the afternoon we have several different examples, a little bit more sophisticated, in which we try to better understand. Of course, it's actually something impossible for you. I mean, there are always exceptions, but I mean, it's difficult in 3 hours presentation to make you an MPI programmer. But I do hope to give you at least a few hints to stimulate your curiosity and to see what you can get out of this paradigm. That is, by the way, is actually still one of the most important. Question for you: how many of you knows MPI? No one. How many of you use MPI program, parallel MPI program? Okay, one. All the other are actually completely new stuff. And what about OpenMP yesterday? Is the same, or there was a little bit of experience in the audience about OpenMP? No. Okay, so you are.
Sorry, there is a new exercise 06, which is a challenge for you, something that you can try, and with the assignment in the code. So I wanted to.
Yeah, no, so we are plenty of exercises there, so there is a lot of interesting stuff to do. I think that we have to do the second edition just to do the exercises. Okay, so this is the agenda. So introduction to models for parallel programming. So just we will focus a little bit on both shared memory and message passing, and then we move on message passing paradigm. And to write message passing paradigm parallel program, we just use MPI, and so we will introduce MPI, that stands for message passing interface. We will discuss a little bit about the most common MPI implementation that you have here, and then we start writing, compiling, and running, and understanding how to run an MPI program. So, just a very short recap. Modern parallel architecture, we have two basic architectural schema. Okay, so the distributed memory and shared memory. Okay. Till the end of 90, this was quite different approaches. Now, within any high-performance computing platform, okay, we have a mixed architecture. So it means that, as you are very much aware after today's playing with the nodes of the cluster are shared memory machine. In particular, they are NUMA machine, non-uniform memory access, but then they are linked together and so we can have also distributed memory approach. So we can run within one single node in a shared memory approach, and then we can put together more than one node, we can cluster together more than one node, and we can do distributed memory. So originally in the 90s, these two main programming paradigms emerged just because they were dictated by the hardware architecture. When you have a shared memory machine, in the 90s, it means Cray, XYMP, and other kind of large workstation. We have shared memory. They used to call it data parallel. It's no longer used this term, but in any case, we are speaking about shared memory. That means exactly what Luca yesterday explained very well, that we have a single memory view, and I stress a lot on this point. We have a single memory view, so for any processor that you have, you can see the memory as a flat, okay, from let's say, from the theoretical point of view, and then you create threads by means, for instance, of OpenMP, and these threads can actually directly access the whole memory. We can share a lot of data. We can also have our own private data for the threads, as Luca explained. Distributed memory is a completely different approach, because distributed memory means that in order to access the memory of another processor or another process, you have to explicitly ask the process to give you access or to give you some messages or the data stored in the location. So all the processes could directly access only their local memory, and only this is actually, and so the memory that you can see from a process is just your local memory. If you need some other data that is actually in another place, you have to ask the other process, okay, and you have to send a message that is received, and then they answer you. Okay? So, well, this is actually a little bit messy. Let's the animation. It's really easy to adopt a message passing scheme in a shared memory computer. So you can use on a shared memory computers MPI. No problem at all. Just because MPI is actually spawning, is actually a bunch of parallel processes, okay, that runs on your machine. Each Linux process has its own memory, and so you have your private memory, and so you can easily, and actually many of you actually probably will use a larger node like the one that you have on the cluster with an MPI approach without any trouble. Okay. The other way around is actually very much complicated, because it means that you have some additional software that provide you a vision, okay, of a shared memory machine, even if the memory is actually distributed on different nodes. There are quite expensive software that bring together the memory of many different nodes of a cluster and show them as a unique shared memory. But these actually are expensive, and especially not so efficient, of course, because again, you think to have a shared memory approach, and then you try to access a location in the memory that resides not just on the local cache, not just on the local RAM, not just on the RAM close to your other socket, but on the RAM on another node. Why do they survive why do such independent software vendors survive? Just because there are some software that is actually thought to be shared memory, and actually sometimes better to build a small cluster of nodes with a relatively large RAM and put together by means of the software than buying a machine with the amount of RAM that you need to run your application. Typical situation is actually, I heard about this there is a company that is doing cars, something like that. Yeah, probably Dacia or something like that. They bought one of these large RAM machines, something like in the order of 20 terabytes of RAM, just to store online in RAM their database. Because the database is too large that they can't actually think to have, I mean, they are using it in a very intensive way, and so if they start storing on the disk, they are too slow. And so they have to keep it all in RAM. And to keep all in RAM, they need a lot of RAM. Okay, and so they have two options here. One, to buy this incredible machine, extremely expensive with such an amount of RAM, or just to put together a few nodes like the one you have, 3 terabytes, and then buy the software on the top of it. The cost of the application, so the database, is so high, okay, that hardware is actually nothing with respect to that. And so there is also room for people that try to bring together things like mimic this kind of approach. In any case, for scientific computing, no way. Shared memory actually across nodes is not a very good idea. Okay? The other point is actually that here is actually about the paradigm on different architecture. Here about how you can write and how you can design a program using a message passing scheme. Okay? So it's relatively easy to design a program using the message passing schema and then implementing the code by means of shared memory. Okay? Relatively easy. Not so easy, but relatively easy. So what you can think is actually, I am a problem. I have to design a parallel approach to it. I will try to design it using MPI, and then I can implement it on a shared approach. Okay? The other way around is actually much more complicated. So the point is actually that message passing is actually a very nice approach because it allows you to understand exactly what you want to do, and you are in full control of all the operation of in your parallel application. Of course, this has a drawback that it's much more complicated to code, okay? Because actually you have a full control of everything. Yeah, this is actually another important point about the programming environment for the two class of parallel program. When you have using message passing, we will use a standard compiler, GCC, Intel, whatever, but we need a communication library that in our case is actually an MPI implementation. On the cluster I saw that you have OpenMPI. We still have to understand if Intel MPI is available, but there are many different of them. And then so you compile the code as you compile your serial code, you link a library, of course, and then you run the code. But the run the code means that you have to have another additional program that allows you to spawn how many MPI processes you want to run on your parallel machine. And this is actually the MPI run command that you have to use. There is a standard. No way. This is the standard MPI. And I will comment on that. On data parallel or open or memory shared is different. We need an ad hoc compiler because yesterday when we compiled the code, we saw that always we add an additional flag. -f OpenMP, -q OpenMP in case of Intel. And so the compiler should understand from the beginning that you have some directive and some pragmas that wants to make your program parallel by means of shared memory. Once you have done this, you are done. The program can be run the same way you run a serial program. The only difference is actually that you can control by means of many different environment variables the behavior of the program. OpenMP plays, OpenMP num threads, the most important, how many threads do you want, and then OpenMP plays and all the things and techniques that we saw yesterday. Also here we have a standard. While here we have a clear, unique standard, here we have OpenMP as a standard, but life is a little bit more challenging and sparkling. There are many other products that are coming out, and they are so we have OpenACC, we have other stuff of this kind. OpenMP that is now at version 5 seems to be the standard, but it's not actually the capital. I mean, it's not actually the unique standard in a sense. So, I mean, learning OpenMP for sure is actually the right way to start, but keep in mind that there are other tools and other products as well. Okay, so architecture versus paradigm. We already discussed this. On a shared memory computer, we can run a shared memory application without any trouble, and we can also run a message passing algorithm without a message passing program without any trouble. On a distributed memory computer, we can just run message passing unless we have something that makes this machine behave like this one. Okay. Yeah, so this is actually a short summary. Architecture distributed versus shared, programming paradigm, message passing, shared memory, parallel programming model. Well, this can be taken with precaution, with some caveats. Parallel programming model, generally here we are speaking about domain decomposition. It's quite natural in the idea that if you have a distributed memory machine, you distribute your domain that you want to simulate. Like for instance, I don't know, in a computational fluid dynamic code, you have your grid, and then you can assign a portion of this grid to other stuff. Or for instance, in a molecular dynamic simulation, you have your box of particles or molecules or whatever you are simulating, and you divide it and you assign each portion of this box to a different domain. The same for astrophysics stuff. On shared memory, sometimes it's better to do a functional decomposition. That means I have a thread that is taking care of reading, I have a thread that is taking care of writing, I have a thread that is taking care of doing this particular subroutine, and this thread's doing this other subroutine, if you are allowed to do that, of course. If you don't have a problem with that. I'm not so in favor, don't take this like the truth, okay? But take into account that this could be. Okay, now let's move now on message passing. I already said the parallel program consists of separate processes, each with its own address space. So the memory is local and is private to the process. You, as programmer, need to manage the memory by placing data in a particular process. You say, I have this array, and this array will be stored there. Okay? Data are sent explicitly between processes. Again, if you need to write data on another process, you have to send a message. Okay? And you, as programmer, take care of doing this kind of memory motion. We have the data distribution. The initial data distribution is done by the programmer. So suppose that, again, just to make a very stupid example, you have a very large array that doesn't fit into the memory of your node. Okay? So you do, okay, let's do a message passing approach, and let's use 2 nodes so I can store my array. Okay? I have to split the array in some way, half on one node, half on another node, but this is actually your task. So it's not done automatically by anybody else or by the compiler, whatever. So you say, okay, I have an array A, and so I split it in a part on one processor and a part on another processor. And then when I have to know what is happening here, on this particular location of this array, from this guy, I have to ask this by means of messages. So data distribution is again managed by programmer, and then we have the so-called collective operation. What is a collective operation? A collective operation is actually an operation, a communication operation, that says, all together now, let's do this operation. The most simple collective operation, a barrier. Suppose that you have 32 cores running. Okay, at a certain point, each core says, call barrier. Let's wait here till everybody reaches this point. This is a barrier, and this is the most simple collective operation because it involves all the processor. But you can also define collective operation on a subset of processor. We will see later a little bit about that. So collective operation can be run on an arbitrary set of processes. This is what I mean with distributed memory and shared nothing approach. I have an array here, and I have the element A10, and then I have an array here on process 1, process 0, and process 1, and I have an array that is called again A10. I'm perfectly fine with that. Remember that A10 are completely 2 different variables. Okay? And so if you want to know this variable, you have to send a message. Okay? And you have to store in a different location, because the value can be completely different. Okay, is it clear this? This is shared nothing. Okay, so we start understanding how to move. So we have to write messages, we have to receive messages, we have to store the data on different processes. And so we need something that helps us to do, and this is done by means of the standard, a message passing library specification. That is actually a quite complex now, because we have now version MPI 3.1 with a lot of fancy stuff that probably we can't, of course, touch during this short presentation. But in any case, is actually a model that describes a way to send messages around on a computer. Okay, is quite extended, is a specification. It became a standard, but it's not a language or compiler specification. So you can have an MPI implementation in any language and using any compiler. is actually was thought to be for parallel computer, for cluster, for a heterogeneous network. It's actually fully featured and designed to provide access to advanced parallel hardware for end user, library writers, and tool and developers. So there are a lot in this standard, in this specification, but it's still a specification. Then, so if you say, give me MPI, I just give you a bunch of pages, actually quite heavy, thick this way, in which you have all the specification. If you want to send a message, you have to do this and this, these are the parameters and so on. So a quite boring reading, okay, of course. And who cares about that? Well, who cares are just the people that implemented the specification, and so we have our implementation. So MPI is a standard, and the actual implementation of the standard is demanded to the software developers of different systems. For instance, Intel provided its own implementation of the standard, okay? And there are many different implementations. I mention here just 3. The first one is MPI-CH. That is actually the original one. MPI was started at Argonne National Lab by Bill Gropp in '92, and they defined the standard, and then also they published the standard, but they published also the first implementation of the standard, MPI-CH. And in the 90s, MPI-CH was the standard, the implementation. Then it came out something called LAM-MPI that then merged with another stuff, and then now we have OpenMPI that is actually the standard, currently the standard for people that don't want to buy for Intel MPI, because this is a commercial implementation. Both of them are actually free of charge, and you can download and install on your computer, and you can have your MPI implementation on your laptop, and you can play on and play all the exercise also on your laptop, of course, because your laptop is actually a shared memory machine, and you go for that. By the way, you don't even need, I mean, now all the laptops have more than one course, of course. No, but you don't even need more than one course, because, I mean, you can mimic MPI just because you have more than, you just spawn a few processes that will share your CPU. Okay, and this is perfectly fine, and you can do a lot of interesting stuff even in this in order to test, implement, check, and see if your code is actually working correctly. So without wasting important cycle on a high-performance computing platform, you can start developing and checking a few things also on your laptop, and it is still perfect. If you keep in mind, of course, that the number of processes is something that you can assign at runtime. Because if you think to write a code that always needs 2 cores, it's not really very much portable, but it's no more the case. All the good scientific and parallel programming are actually quite, can actually allocate any kind of processes. This then has the consequences to see what is the right number of processes to run a particular application. And we come back to this, and and yesterday also Luca mentioned about scalability. No? So we have to understand which is the right number to run your application. Okay? Perfect. So we have an implementation. By the way, we are using OpenMPI, okay, here. Today, I compiled the codes by means of OpenMPI. OpenMPI, maybe I have, if needed, maybe I can add some more slides about OpenMPI, because it's quite interesting project, but for the moment, let's move on. So MPI is a library. So our operations are performed by calling some specific routine of this library. And we have basic definitions that are in MPH in C, C++, this MPH-F for Fortran 77, Fortran 90, and if you are a Fortran 90 programmer, you may know that MPI, you can use module, and so you have also the MPI module for Fortran 90. Who cares, let's say. So in any case, it's like, a standard C library or a standard Fortran library. You have the headers that you have insert in your code, and then, of course, what you have to do is actually compile with this header and then link against the library. Which are the basic features of the MPI programs? Well, we have 4 classes of features. we have calls used to initialize, manage, and terminate communication, and this should be actually understood, and we will see a couple of them. Well, we will see what we need, actually, all of them, actually. Then we have calls used to communicate between a pair of processor, what we call pair communication or point-to-point communication. So from one guy, I want to call this guy to give them some data or to receive some data from him, something like that. So this is actually point-to-point communication or pair communication. And then we can also have collective communication that are calls used to communicate among a group of processors. We will see a few of them. There is also another important class, but we don't have time to touch it. It's actually that by means of MPI, you can also create your own data type. And so, again, why do you need your own data type? Because sometimes maybe you don't want just send a bunch of floating point numbers, but you want to send to another processor a complex data structure that contains more than one information. Why do you want to do this? Well, because maybe you want to minimize the latency in the communication. No? So you want to pack all the stuff together, and then we have a large pack you send it out on the network. Remember that this, again, is important. This also depends very much on which kind of network you have. Remember that you have a network, okay, that we saw roughly 3 order of magnitude slower than the RAM or the caches. So when you send out data here, it takes forever, okay? And there is a latency associated to the fact that when you want to send a message to another node, okay, let me now do a better picture here, okay? I have my node now, and then another node that are connected by means of a network. In our case, here we have FDR network, InfiniBand FDR, 56 gigabit per second, okay? That means that you have a bandwidth, the overall bandwidth around 7 gigabytes per second, but actually you can measure something like in the order of 6 gigabytes per second. Okay, remember that yesterday we were measuring the bandwidth between one core and the RAM, and we were around 16 gigabytes per second. So it's lower, a couple of times lower. But then the other point that is actually dramatic is actually the latency. Latency is actually the time it takes to open the channel to communicate. And we will see, and the latency here for the FDR is something in the order of 1 microsecond. That's very good latency for the network, of course. It is quite expensive, the FDR network that you have. It's actually, so you have 1 microsecond here. Latency here, you remember, the latency that Luca mentioned is actually around 100 nanoseconds for the RAM. Okay, so we have an order of magnitude in latency, if you are lucky enough and if you have a very good network. Okay, and then you can share maybe this latency and this bandwidth with many different processes that you are sending around. And so things are actually getting up. So this is actually clearly a bottleneck, and you have to take care about that. Because if you run a parallel program and you say, okay, here I have, for instance, 8 cores, okay, and here I have other 8 cores, okay, and then you say, okay, I run 8 cores here, then fine, now I need more than 8 cores to complete my computation because I need more RAM, I need to go fast and whatever. You can add 8 cores, but don't expect that the scalability within the node is similar to the scalability across the node. And sometimes you can also think to say, okay, if I have 12 cores, maybe it's better to say 6 here and 6 here instead of 8 here and 4 here. Just because you have a sort of imbalance, and the communication can be completely unbalanced. So again, testing and benchmarking the kind of the kind of performance that you can get is actually extremely useful. And so that's why creating a data type can be useful, because you say, I have to send out all the information and I have to pay this penalty in terms of latency. It's better to organize one single message and send it out, instead of continuously keeping sending small messages one after the other, because every time I have to open the channel and I have the latency cost there. So there is always trade-off. That's why we have create data types. Okay, a lot of other stuff. We don't really mention all of them. I would like just to tell you that we have also parallel file system I/O. That is actually one of the main topic I play with. So we are actually working a lot on MPI I/O to optimize input-output operation on a parallel file system, on different parallel file systems. And it's actually a lot of fun for us nerds on this, and a lot of other stuff. Okay, you succeeded in writing your code, and now let's compile it. So there is no standard. The MPI program, the MPI standard doesn't define the way you have to compile the code. But generally, due to the fact that you are actually linking a library, what you have to do is actually to specify the appropriate include directory, because I just insert my mpi.h header file, no? And then I have to specify also the MPI library that should be somewhere in minus capital L, MPID, slib, and blah, 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 and then minus L MPI. So, a little bit complex. All the implementation provide the so-called MPI compiler wrapper that automatically find the include files and the include directories, include the right files, and link against the right directory. Generally, this is called MPI CC or MPI ECC or MPI something. Okay? On our cluster, if you load module load OpenMPI, you can then try to type MPI, and you will see that there is an MPI CC, an MPI Fortran, MPI Fortran 19, and some other wrapper for other kind of for different languages. Okay, so it's simple to compile the code. Writing the code is complex. Compiling the code is simple enough if you know where to find your MPI CC wrapper, the MPI wrapper. Running MPI programs is still not specified by the standard itself, okay? Because, for instance, it's the same like Fortran. Fortran standard does not specify how to run a Fortran program. It specifies how to write a program. Again, implementations here helps a little bit, and you have command like this, MPI run or MPI exec. Okay, and generally the most important option of this command is this one, -mp. Okay, where mp is the number of processors that you want to use. So if you do this way, MPI run -mp4 a.out, it means that it takes the a.out parallel program and spawn 4 different processes, okay, that start running. Okay. Then there is a little bit of complication, but now things are a little bit simpler, and with MPI run you are okay. Of course, what is happening that when MPI run -p 4.8 and you run and you have assigned this machine, of course the 4 nodes will be assigned to some cores here, if you have 8 cores each. You can control with a lot of options where to put your MPI processes. So maybe you want to say, okay, let's run on 4 cores, but I would like to have 2 cores here and 2 cores here. Or I want to have 1 core here, 1 core here, and 1 on other nodes. And we will do some experiment later just to measure the latency and the bandwidth of our network. Okay, so we will place 2, we will run a small example that say MPI run -mp2, and then we will place the 2 processes within the same socket, across 2 sockets, okay, and then across 2 nodes. And we will try to estimate what is the latency of your communication, the latency of the bandwidth of your communication, and you will see quite striking differences. Okay, so MPI run is actually your best friend in order to get most of our to exploit performance of your parallel program, because you can control where things can be placed. Okay. Okay, now let's start writing MPI program. Yeah, I already told you this. MPI standard include routine for the following operation: point-to-point communication, collective communication, process group, process topologies, and environment management and inquiry. And we will see a few examples. In any case, MPI can be used just knowing these 6 calls. Everything you can do with MPI, with a lot of effort, can be done just using this, because what you need is actually to initialize your MPI environment, MPI init, that is actually present in your MPI program, the first call, the first routine that you have to call. Then you want to ask the system how many processors you have, MPI com size, and then you would like to identify which out of this n processor that you have I am. Okay, so who am I and how many processors I can run on. You can easily see the equivalent in OpenMP. No? OpenMP num threads, OpenMP. What is OpenMP? I forgot. Well, in any case, you have two information that tells you where you are. And then we have the MPI finalize to close MPI, that is actually should match the MPI init. And then we have these two red in red function that is actually a send and receive. As I told you, you have to send messages and then you have to receive messages. Once you have a mechanism to send and receive messages, everything can be done in principle. Okay. Then of course there are a lot of other MPI routines that allows you to to avoid to write by your own by means of send and receive, for instance, a barrier mechanism, no, and so on. So this is actually the basic, but for sure should be almost enough if you are brave. Yeah, if you are brave enough. Of course, there are plenty of other routines. MPI, the standard MPI 1.2 has 150 or 120. MPI 2 has something like in the order of 200. MPI 3 has even more routine that allow you to do whatever you want, of course. But of course, but this is actually quite sophisticated usage of the MPI. Okay. As a tradition, let's start writing hello world in MPI. Fortran and C. Let's focus on C, even if I'm not really a big fan of C language. But in any case, you can see main int, I define the rank and the size. Then I call the MPI init. And then I do an MPI common rank. And I have an MPI common word here. And then I have an MPI common size. And then I print I am rank of n processor. I finalize and I return. Okay? In Fortran is more or less the same. There is a difference here in Fortran. I don't want to go into very much detail, but I have a call MPI. I have to define an integer r here because you see the error, the code error is always part of the argument of the subroutine in Fortran, while in C you don't have it. But okay, this is the situation. What is actually, so very simple, whatever. So what should we expect from this program? Well, on this program, if we run this program on 4 cores, we should see something like I am one of 4. I am 2 of 4, and so on. Okay? Is it clear? Let's discuss a little bit more because I want to go on because I think I have. Okay, perfect. So, a few notes on the program. All MPI programs begin with MPI init and end with MPI finalize. Start MPI, close MPI. MPI common word is actually an important data type that is defined by MPI H in C or MPI F in Fortran and designates all the processes that take part of your program. Okay? So MPI common word is a default value that if I try to do an MPI run minus MP4 is actually involves all the 4 processors that I'm starting playing with. Okay? Another important point is this, that each statement executes independently in each process. So you have a program that is compiled and is executed 4 times on 4 different processors as independent process. So you can go on. So, okay? And also the printf and print statement is actually completely independent. Input-output is not part of MPI-IO. MPI-IO is part of MPI-2, but still in MPI-IO you don't say that, you don't have any way to control the printf and print statement. Printf and print statement are actually C or Fortran statement, okay? And so the program is actually execute one after the other independently. So if one process, if processor 0 is actually a little bit slower than processor 1 because processor 0 has to share a node or its computational core with another application, whatever it means, okay, it can be that actually the order of print IM 1 of 4, it can be completely screwed up. Okay, there is no way to guarantee that there is a specific order. If you want this, you have to implement by yourself, communicating and saying, which are you? So, okay, now let's have a priority queue. You start first, and so on and so forth. Written this way, it's actually this way. So the output order is completely undefined. Okay, so as a consequence of the requirement that non-MPI statement execute independently. Okay, so these are the 2 routines. Let's take a look a little bit in detail. So MPI init, integer argc hr argv. For Fortran, call MPI init IR, where this actually this code error, and then you finalize this way. Quite simple. And these two routines should be called by all processes, and no other MPI calls are allowed before MPI init or after MPI finalize. If you call an MPI routine before MPI init, you got an error. This is quite simple, and now let's come to the communicator. That is actually what I told you before. The communicator is a variable that identifies the group of processes, okay, that are allowed to communicate with each other. So by default, the MPI common word is all the processes that you launch in this execution. So MPI communicator, if you run with NP4, is actually 4. It's actually include the 4 processor, but if you run with 8, it will include 8 processor. Okay? So this is actually the default communicator that includes everything. Okay, you can define your own communicator and include a subset of processor, and there are interesting applications for this, but we don't have time to discuss this. And then all MPI communication subroutine need to have a communicator argument. And of course, you can define as many as you want. Just to give you a feeling about what you can do with a different MPI communicator and why you need a MPI communicator, let me just tell you this short story that we are actually facing in our intensive I/O application. We have a bunch of nodes that have, let's say, 8 nodes, 8 cores, okay? And what we are trying to do is actually that we are trying to do writing and reading in parallel, okay? And so here we have again a network, and then we have a file system here, okay? And so we are actually writing a file in parallel. So each core write its section of the file, okay? So I have a file. Suppose that I have a very simple example. I have an array, and so I split the array by means of MPI in eight different private region, and then I ask this guy to write this region, the first region, at the beginning of the file, the second guy, the second region, and so on and so forth. Okay, so this is a parallel approach to MPI to I/O. MPI I/O has a lot of routines that allow you to do that. Perfectly fine. What is the trouble here? Again, that we are writing 8. Suppose, let's say 4 nodes here, 4 cores here, and 4 cores here. So I'm writing at the same time 4 operation on this card, 4 writing operation on this card. So I'm sharing this card 4 times. no? But among 4 different writers. And the same here. So I am actually sharing this card, and so my performance are not so good. So what is a better approach? Well, a better approach would be just to say, okay, instead of writing all, let's actually collect the information on a guy here, okay, on one node, on one core within the node, okay. Let's actually collect all the data here, do the same here, okay, and then ask this guy to write half of the file, and this guy to write the other half of the file. What is happening here? That I'm actually having one single operation in writing, okay, and it's actually, it could be much better. Even because splitting this operation is actually easier, because instead of writing this small part of code here, I can just copy this small part of the code in an area by means of a message here. How can I implement this? Well, I have my communicator that involves all the 8 cores. And then I have to define my private communicator within this node that involves just these 4 nodes. And so I can have communication between these 4 nodes in order to confine the communication within this node and to confine the communication within this node. And this can be done exactly by defining different communicators. That's actually the idea that we have behind. Okay, here I'm speaking about 8 cores, but when I speak about we are running the code on 512 cores, that is actually quite a large number, and we have machines that have 48 cores or stuff like that, so there is an overhead associated with the MPI operation that is actually too much, and is not actually the right way to go. So we have to rethink a little bit the way we are doing input-output operation this way. And for this we need MPI communicator. I told you that I like MPI-IO, sorry. Okay, the other 2 important stuff is actually identifying the size of your communicator, okay, and the process rank, okay, how many processors are associated with the communicator, MPI common size, what is the ID of the processor in a group, MPI common rank. Okay, as you can see, I have the MPI communicator here, and I have an integer, okay, as in this call, and again for Fortran I have the error. The error control, and the same here. So the output is the size, and the output is the rank. And so I think this actually is quite easy to understand. For 8 processor, I have size 8, and if I am actually landing on this processor, I have rank equal to. Okay. Sure.
Output of the cycle is then again fed back into the input. So is this an I/O process?
Sure.
Self-consistent cycle.
Yeah, I mean, of course, what is doing what is doing Quantum Espresso is actually that in the self-consistent process, it stores sometimes the wave function just to be sure that you can restart again if in case of trouble. And this is done actually. I don't remember the way they are doing right now. At the time I was looking at the code, it was actually in a serial way. So there was a guy that collected all the information. Well, no, it was done in a parallel I/O, in a parallel way, but just any single processor open its own file.
Now I think it's only written on user input, because I think what I read is that the overhead became too high.
Yeah.
To write it at every step. So now.
You can define the number of iterations that you have. But I mean, when at the beginning it was actually a very slow process, and sometimes you need to save. Yeah. There are several ways to save, because you can save the wave function, but also you can save just the charge.
Right.
And this is actually a little bit different, and there are tricks behind that. I am not aware about any MPI I/O implementation in the moment, but I can be wrong on that. We are working with the code that I'm mentioning here is actually climate modeling, a climate model, so that simulates the evolution of the climate, and it runs on a very large domain, and we split the domain this way. And it's actually quite IO intensive because it's producing a lot of data for that. And so we have to optimize a little bit that. Because otherwise, at a certain point, when we do the scalability, it scales very well on a very low relatively low number of cores, but when you reach 512 and stuff like that, all the time is actually spent in writing and reading, and we have to fix it in an appropriate way. Okay, so now we can move on and go for learning how to send a message. So to send a message by email, okay, via mail, standard mail, snail mail, whatever, you need an envelope, of course. You need a piece of paper in which you write your message, so the message. Then you need the destination address and the sender address. Not strictly needed, but it's better to put it. Okay, so that's actually the way you communicate by means of an envelope. And MPI is exactly the same things. Okay, so I have a process that sends data to another process that receives data. So I have now to define a few things. How will data be described? Which kind of data I'm sending? Well, this is actually, I need a data type. If I send an integer, I need an integer data type that should be defined by the routine that send out the message. How will the processes be identified? Well, to do that, I need a rank and common. No? And then, how will the receiver recognize the message? Well, I can tag the message just to say, okay, this is actually exactly the message I want to send to you. So you can check this tag that is actually exactly the message that you are sending out and I'm supposed to receive from you. And then, what does it mean for this operation to complete? Blocking or non-blocking? This is actually a key point. Blocking operation means that I'm sending you something. Until you tell me something that you receive, I'm not going on. Okay, so I'm waiting for your callback. Phone call, okay? I want to send you a message by phone. I call you. Until you answer the machine, okay, I can't do anything else. Okay, and then when the point is actually here that when you answer the machine, you answer your phone, I can say, hello, listen to that. And then I can go doing other stuff. Or I can say, hello, listen to that, and then I close the communication. Again, a different approach. Okay, non-blocking means that you can go on. And this is actually typically the envelope process, the old envelope process. You go, you take the envelope, you fill in the envelope, and then you go to the mailbox. You put your envelope in the mailbox and then go back to do your stuff. Nobody knows if this envelope reach you. And if you try Italian mail service, you can have you can wait for a while, and the latency can be really high. 7 days to come from Trieste to Trento, a letter, just to tell you very recently. Okay. So, but this is actually the way. So I have blocking and non-blocking operation, and this can be done in MPI. Let's now focus a little bit on describing data. So the meta MPI data type is the data in a message to send or receive that can be described by a triple, an address, a count, and that kind of data type. So I will send to you tens integer. No? An MPI data type is defined this way, predefined corresponding to the data type for the language. So for instance, you have MPI int, MPI double, MPI float, MPI a lot. We will see a list. If you don't have it, you have to use. You can say, okay, instead of defining a single MPI, I can define a contiguous array of MPI data type. You can even have a strided block, and then you can also build your own data type, as I mentioned before. Let's focus here. For the time being, actually, probably almost 90% or 95% of the codes that I know are actually built using predefined data type. Yeah, 90% I would say, they're around. What about you, Luca? Are you using your own data structure in Gadget? Sometimes. but the majority are just a standard data type. Yeah. Okay? And then there are these MPI functions that allow you to construct your custom data type, in particular one for subarrays, but you don't want to see this kind of stuff. These are the Fortran MPI basic data types, so you have integer, real, double, precision, complex, and blah, blah, blah. Okay, that is actually the equivalence here. By the way, MPI packed, MPI byte is not actually available in Fortran data type, but you have this extra data type. And this is actually the C data type, the MPI basic data type for C, MPI char, short, int, long, unsigned, unsigned short, and so on. Again, byte and packed are actually not mapped directly on the language. Okay, the data tag is actually another important thing, that messages are sent with an accompanying integer tag that allow you to identify correctly the message. Okay. And so you can actually say, okay, suppose that you are receiving a lot of messages, okay, you can say that you can tag a message and say, this is actually an important message, this is not so important, or this is actually for this part of code, and so on and so forth. So you can have a quite good flexibility to define your tags. Okay? Of course, if you are not interested to know the tag, you can receive and say MPI any tag in the receiving call, and you will receive from any tag, and you can't do any kind of analysis of the tag on the message that you are receiving based on the tag. So this is actually our first send message: MPI send, buffer, count, data type, destination, tag, and communicator. Okay, buffer is actually data to send, so it's actually an address in the local memory where I actually load my data to send. Okay, then I have the number of data that I want to send, the number of elements in the buffer, the data type, which kind of data types in the buffer, the destination, the receiver, the tag, and the communicator. Okay, one of the most common problems is actually that sometimes you actually call an MPI send, you give the buffer, and then you made a mistake in the data type, and this can be quite heavy because, for instance, you can say, okay, you forgot that you want to send a double, and you say just MPI float, and you are just send half of the byte, and this guy reads just a list of bytes, and you send out of the byte, half of the byte in a float format. Okay, so be careful about that. Well, this is a typical problem that you can have. Of course, any send message should be matched by a receiver. Okay, and this is actually the way to receive the file. So MPI receive, this is written in Fortran, sorry, so I have an error here, but so it's quite simple to understand. Buffer, count, data type, source, tag, communicator, status, and an error. A few words here: source is the sender, can be set as MPI any source. So while when you send, you have to tell where to send things, when you are receiving, you can say, well, I have to receive something. I can also say MPI any source. So receive a message from any processor within the communicator. Okay? The tag is the label of the message. Can be set as MPI any tag, again, because I can receive any kind of messages. And then finally, you have the status that it actually is an integer array with information on the message in case of error, so you can check what's happened during the communication. Okay? So this is actually the way it works, and the status actually is a data structure allocated in the user program, and it has a little bit of information. For instance, you can, in C, you can do something: receiving tag, status MPI tag, receiving from, status MPI source. So you have a lot of information about your message. And then, for instance, here you have an MPI get count. You pass the status, you pass the data type, and then you receive the count element that you got. So in this way, for instance, this is quite useful to check that if the data are completely and correctly and safely sent and received. And this is, again, the Fortran equivalent. So this is actually a very stupid example, a little bit more complex. So we are call MPI init, call MPI common rank. If I am rank equals 0, I can say buffer equal 33. Okay, and then I say call MPI send buffer one element of MPI integer. to processor 1, tag is 10, MPI communication word, and the error. And then if I rank equal 1, then call MPI receive and blah, blah, blah. Okay, on how many processes can I run this program? There are 3 answers here. 0, that is wrong. 2, and as many as I want. So there are 2 answers. As many as I want or 2? As many as I want. Of course. As many as I want, because I run, and if I have an MPI common rank that says I have 300 cores, only these 2, only rank 0 and rank 1, does anything useful. I mean, does anything. The other, just to say, arrive here, they call this, they say, if rank equals 0, I'm not rank 0, I'm not rank 1, call MPI finalize, go home. So, you know, so this is actually a typical MPI code that is actually hard-coded the number of cores, the number of processes that does useful things. Very useful is actually quoted here because, I mean, but you are not prevented to run it. You can run it on thousands of cores, of course. No?
But it won't change anything.
It won't change anything, but you can still run it, okay? It's not something that maybe you can say call MPI common rank and then you say if rank is not, if MPI common rank greater than 8, crash. Now if you have something like if MPI common rank, MPI common, not rank, the other node, the number of nodes, and you can put a counter on this and say if the number of nodes is greater than 8, stop everything with an error. Okay. Here there is no error, and so you can run whatever, and just the 2 first cores, the first 2 processes does something. Okay. So just to understand that is actually the number of cores, the number of processes. Sorry, I'm not really very much precise in my language. I'm always using cores, processes, processor, process, and whatever. So process is actually the program that runs, okay? Is a MPI process is a piece of software that is running on your machine. I identify sometimes the process with the core, and sometimes I identify the process with the processor, okay? For me, it's just because, I mean, they are similar, but again, the right way to say is actually that I have MPI processes, and I can spawn MPI processes as many as I want, okay, on any kind of resources. And this is actually, again, true on a single machine. You can spawn 1,000 processes on one single core. What is happening there? Well, it's happening that actually the operating system is actually getting crazy because it has 1,000 processes on a single core and start playing with them, and probably what you will see that is the overall efficiency of your program is quite low because there will be a lot of system time, because a lot of work to manage all these processes has to be spent by the operating system to manage all this mess that you created in this way. Okay? Okay, communication mode, as I told you, 4 different send types. I have the standard one that is MPI implementation here, decide which is the best strategy. The synchronous, that is actually, it is completed when the receiver acknowledges the reception of the message. I call you by phone, I tell you everything, and you say, okay, thank you very much, gone. Synchronous. It's a blocking mechanism, this one, okay? Till the guy tell you, I received everything, I'm not done. You can't do anything else. You are on the phone, okay? Then you have buffered. That says the following, that say, okay, I'm actually, this probably is actually something like a WhatsApp communication that you send out, okay? You see that the message was correctly sent out because you have the double click, but not green, and then you will see the double click green when you read the message. But the message is out on the net, correct? Is it correct? I mean, I'm interpreting correctly WhatsApp because I'm not actually quite. I mean, according to my daughters, I'm actually a very poor user, WhatsApp users.
One tick sent, two ticks received in the
Perfect.
phone, but not seen.
Exactly, and two ticks green,
Exactly.
received and read. Exactly. So okay. So buffered is actually I send out, and that and it's somewhere else, and I don't know where. Okay. So one single tick. Thank you for the clarification. And then ready requires the receiver to be already waiting for the message. Okay. There is one single receive type that is actually I'm receiving. So this is actually complicated. I don't want to focus too much on this, but it's actually important to understand exactly the blocking and non-blocking, because this has a different, can have a quite interesting behavior and quite weird behavior as well. So when is send instruction complete? When it's safe to change the data that we send. Okay? So it means that I send out the data, okay, and then I'm allowed to change the data. Remember that data are private, so I can do whatever I want on my data. And so this is actually when I send instruction complete. When is the receive instruction complete? When it's safe to assert the data we received. Because I know that no more data are arriving and is actually completed. And so for both communication, send and receive, we have these two choices. A blocking approach, start the communication and wait for it to complete, or start the communication, return control to the main program to do other stuff. And this is actually the modern approach if you have a very complex code in which you do a non-blocking sending, and then once you send the data, then you start doing other stuff. And so you can overlap communication with computation. Of course, the non-blocking approach requires to check for completion before you can modify, assert the send receive data. What does it mean this? That you say, okay, I'm sending out your data, okay? Now I wait while you are receiving them. I'm actually here doing other stuff, preparing another bunch of data, for instance, to send. Before starting sending the other bunch of data, let me check if you have received correctly all the data. And there are appropriate routine MPI tests that you can check, in which you can see what is happening. Yeah, the pro and cons for non-blocking, I already said non-blocking communication allows a separation between initiation of the communication and completion, and so you can do overlap. You can overlap computation with communication, and is a very nice trick to do what we call the latency hiding. So I'm hiding the cost of the latency because while I'm sending, I'm doing other stuff. Okay, and so it's a sort of you can benefit from that. The disadvantages: the code start to be a little bit more complex to understand, because you have to check to insert the code for check for completion, and it's not easy to understand where is this communication when the communication is completed and so on. So it's a little bit more tricky to read the code. Generally, the suggestion is actually that you start doing all blocking, so you are sure that there are no deadlock, as I will discuss in a moment. Once you are pretty sure that your code is working correctly, start adding if you need and to do a little bit of latency hiding, start adding non-blocking send and receive and match them appropriately. But this is actually generally at a later stage. Yeah, these are actually the communication modes. So standard send, MPI send, standard receive, MPI receive. The non-blocking subroutine is actually MPI I send, okay, and MPI I receive. Then there are the other two, synchronous send, buffer send, that I mentioned before. I mean, they are there, but I mean, generally you can just use MPI send. MPI send is actually more or less the majority of the code works with this way. Okay, non-blocking send and receive is actually this way. MPI I send. You see there is a request here. Okay, that is the identifier of in the communication handler. Okay, by means of this request, you can check if your message has been completed, has been sent completely or not. Okay, so it's actually similar to the send, the blocking send and the blocking receive with just one more parameter that is actually this request. And then you can check them. Well, this is actually the way you can send it, and here is the way you can test the completion. Okay, so you can do an MPI wait by means of req status, and you can check what's going on. So MPI, so request is associated to a call to MPI receive. Status contains the information of the received messages. Otherwise, status could contain an error code. Well, I don't really want to go into too much detail. This is actually the stuff. Okay, before coffee, I think, or maybe let's just study this very simple case. Just understand better the send and the receive, the blocking send and the blocking receive. Look at this small piece of code. Okay, it's written in Fortran, but I mean, I think that you are able to interpret easily. Okay, I have, if I'm rank 0, I will send a data, okay, with the tag 10, and then I will receive a data with tag 20, okay, and I'm sending to processor 1, and I'm receiving to processor 1. The same way is done on the other process. Okay, so I have a process that send a message and then wait to receive another message. Here the same. And what is happening? Deadlock. Why? Deadlock means that the program stays there forever. You know what it means, deadlock, no? So no way to go on this. Why is happening this? Correct. Exactly this. You got perfectly the point. We have a solution. Trivial solution? Huh? Perfect. Well, solution A, solution B. Yeah, solution C. So you got solution C in a moment. Correct. You just, and we are okay. So this is actually a very trivial example, okay? But just to give you to be careful when you have to do pair communication or point-point communication to match correctly the stuff. So efficient as suggested and very well done. Okay, then there is also another way. Do any non-blocking send. Call MPI I send, call MPI receive. This goes on, okay, call MPI I send, call MPI receive. This match perfectly, okay. Be careful that, of course, I have to call an MPI wait at a certain point to be sure that my send is done correctly before going on, if you think that modifying this buffer is important for you, okay. So, and then the solution A, that is actually the most complicated, is actually a buffer send. Because if you say MPI buffer send, it puts the message in a buffer and then returns again, and then it completes. Okay, back in 25, a lot of years ago, when I start writing my code and learning MPI, I just write this element, and it was perfectly running. Okay, and it was perfectly running. Then I modified a little bit and whatever, and at a certain point it didn't work anymore. Okay, and I did a little bit of work, and I discovered that it was perfectly running up to 120K, where 120K was actually the size of the array that I want to exchange between them, between the two processors. I mean, the code was a little bit more complicated than that, but actually the idea was that. That's why these slides are still there, because actually I ran into this problem, and I think it's important to mention. So, till 128, perfectly fine, okay? After 128, deadlock. So, I was actually completely puzzled by this, and at that time I was using, well, you're probably not yet born at that time. I was using the first parallel machine, T3E, at Cineca. I was working at Cineca at that period. And so I went to the guy from Cray, because that was Cray that was providing the T3E machine. There was a couple of guys Craig guy there to give support to the community. And I went there and I say, okay, I wrote this code and your implementation of MPI is completely buggy. Because look, it runs up to 120K, okay, and then it stopped running. What's happening? Probably you made a mistake and there is something wrong in that. So they look at me and they say, well, it could be. And then they start looking around and the answer was, no. The implementation we did is actually, no, the answer was, you are wrong. Because this is the wrong way to do things, okay? It works just because our own implementation buffered, without telling you anything, up to 128 kilobytes. So, what is the lesson learned here? Never trust the implementation, in the sense that do things the right way the standard is actually proposing, and not rely on implementation. I relied on implementation because it was working, but the implementation has a limit for my problem at a certain point. And I run into this problem and I discovered that it's much better to focus mainly on how the standard is working, exchange the send and receive, and go on with that. Okay, what else? I think that we can actually, I can probably do collective operation. That is actually collective routines that provides an higher level way to organize a parallel program. Instead of matching always send and receive, you can rely on collective operation. And then, as I told you, each process executes the same communication operation. And we have really a rich set of collective operation, and we will see just a few of them. Okay, communication involving group of processors in a communicator. I already said group and communicator can be constructed by hand on using topology routines. I already told you the example of MPI-IO. Topology routines are routines that actually ask exactly where your MPI rank is, on which core and on which kind of architecture you are. And so you can do quite sophisticated MPI communication pattern by means of these MPI topology routines. Tags are not at all used because different communicators deliver similar functionality. There are no non-blocking collective operation. They are all blocking. So once you call a collective operation, everybody should reach this place. And this is actually, again, very useful to check that if you didn't make a mistake. Call a barrier. Actually, it's actually quite expensive if the code is unbalanced, but it's quite nice to see that everybody arrives at that particular point in the workflow. And we have three classes of operation: synchronization, data movement, and collective computation. MPI barrier was actually the first one I told you. Very simple. Call MPI barrier, int MPI barrier. Of course, the argument is just the MPI communicator. And exactly, almost never required in a parallel program if it's done well. Actually quite useful in measuring performance and checking if your code is well balanced. What does it mean, well balanced? It means that all the MPI process do more or less the same amount of computation. Okay? And so if you call a barrier and you see that the calling a barrier takes really nothing, it means that all the processes are quite synchronized and they are at the same level. If you call a barrier and stand there forever, it means that some process is doing much more work than the others. And so you have to think how to balance the load among them.
If you run things on heterogeneous hardware, this might be the case.
This might be the case, exactly. This might be the case, and this is actually quite dangerous. My suggestion is actually that if you have an MPI program, never ever run across heterogeneous hardware, because actually it's unpredictable what's going on. There is one single operation. No, there are one single things that you can do on a parallel program that can benefit from heterogeneous hardware is actually a master-slave approach. Well, a master-slave approach is quite simple. There is a master that sends out to slaves a bunch of work. And what you can do is actually that you can write your program in a way in which I give you a bunch, okay, in a round-robin way, and then the first that is completing the bunch receive another bunch. So it could be nice in this way to have a heterogeneous resource, because if the bunch are small enough or not so much large, also the slowest machine can compute for you something. Okay, but this can be done in a different way and a different approach. And of course, you don't have to use MPI blocking operation, because once you call an MPI collective operation, because once you call an MPI collective operation, you're waiting for the slowest one to complete. Generally, this master-slave approach are actually written in different way. We wrote it in Python with a small wrap-up in Python, or even in Bash. It's not so complicated. And we forget about MPI, just because MPI force you to synchronize at a certain point. No, even just the MPI init and MPI finalize is a sort of, well, it's not really a synchronization, but so it's not actually the right way to use this kind of tools, this kind of approach. For master-slave, there are much more nice tools to do that. Okay. So this is the barrier, okay, so yeah, so T0, T1, we call it, all the processes arrive, they are all at the barrier, and then we start again, well synchronized, and see what's going on. Very trivial one. Broadcast is another interesting collective operation. It's actually a broadcast, so one-to-all communication, so the same data sent from the root processor to all the other communicators. In case of master-slave, broadcast will be for sure used. No? You broadcast out. Generally, broadcast is used because there is a root processor that read, for instance, the input file and then propagate by means of broadcast the needed information to all the other processes. Okay, so this is the way it works. So this is a very stupid example of an implementation of broadcast. I don't know if you see it, but I mean, I have on my ID equals 0, that is my root processor. I define an array, A1 and A2, and then I do a call MPI broadcast of this array with 2 elements that are real, okay, and I send it to everybody with what is actually let me just check that the root exactly from what, so the buffer, the number of elements, the type, and where I'm sending, so the root processor here, and then I do write my ID A1, A2, and I will see that for each of the processor participating in this computation, I see the same value here. Okay, same value. Okay, on variable that are completely disjoint, because again we are in parallel. We are in a private in a distributed memory approach. So this real A2 is actually an array of 2 elements on each, a separate array on 2 elements of each processor. Okay, and it's completely independent. At the beginning, I initialize it at the same value for all. And then maybe they will change during the computation. Reduction is actually another important operation, collective operation. Collect data from each process and then reduce the data to a single value, and then store the results on the root process. Or you can store the results on all the processes. This is actually the call. It is MPI reduce, means that you are reducing the results just on the root processor. If I call it as MPI all reduce, I will reduce the operation. Sorry, I will reduce the value on all the processes involved. This is actually the way it's called. MPI reduce, send buffer, receiving buffer, count the number of elements of the buffer, type, the data type, okay. Op is actually the parallel operation to be performed, can be a sum, can be a maximum, can be an average, and so on and so forth. Okay, we will see in a moment better at this point. Okay, just to understand better. And then we have the root, because I have an MPI reduce, so I'm reducing just on the root processor my communication and my error my control there. And then the argument root is missing. Okay, if I take away the argument root, I'm calling MPI or reduce, because at this point the send buffer is different on any processor, but receiving buffer is equal for all the processor, is actually given by the operation, the binary operation I'm performing. These are the reduction operation, maximum, minimum, sum, product, and blah, blah, blah. Okay, and here is actually the point. Again, very stupid. I have I have two array, A2 and res2. On A1 I have 2 and 4, and then I call an MPI reduce A. I will put result in results here. I move 2 reals. I will perform a sum, and I will then do a reduction only on the root, because I do MPI reduce and not MPI all reduce. So on root. And then when I am in root, okay, I will write what I have. Okay, so on root processor, what should I see? res1 and res2 is a sum element by element. Okay, so if I run this on 2 processor, I will have that this number actually is 2 on all processor, because it's defined by the beginning, and this is 4. And so if I sum, is actually 2 times the number of processor for element 1, and 4 times element of processor for element 2. Is it clear? So reduce means that I have an array, okay, that is common on all the processor. Suppose that I have 4 processor, I have an array. This is element 1, 2, 3, 4, and 5. And then I can do a reduce, and I do a sum. I will sum this together. Okay? Is it clear? And if I do an average, I will do the average of these 4 numbers. And if I do a maximum, I will do a maximum of these 4 numbers, and so on and so forth. Okay? Of course, I can also do a scatter, that is, again, one-to-all communication. Here, it's a little bit different from broadcast, because scatter means that I send different data sent from root processor to all other in the communicator. Okay? So the sender just say the send buffer, how many numbers I send, and which is the data type. And then the receiver say receiving buffer, receiver counter, and receiving type. Okay? And I have also the gather and scatter. I mean, scatter is I'm sending out, okay, and gather I'm collecting. And again, this is the way it does. Okay, when I scatter an array, okay, of 4 elements, it means that the first element goes here, the second element goes here in this way. So I'm scattering it. Okay, I'm taking the array, I divide it by the number of processor, and I send out. Okay, and when I gather, is the other way around. So I have that I'm actually receiving a buffer from all the processor, and I put it in a single large buffer on the root processor. Okay, and again, you should also have the MPI, the MPI all scatter and LPI all gather. That means that this is collected on all the processor will have this array. Okay, and so this is actually again a couple of examples, and it's written in Fortran. Oh, I think I have to stop here. Yeah, well, I'm done. Tutorial to play with. So we have a few exercises after. So I think that we can stop here, of course. I will come back and maybe we can comment a little bit more on scatter and gather. And then I have a small example that we can do together during the next session after the coffee break. Okay, sorry to be a little bit late. Okay, so in the last session for this morning, what we can do is actually to play with a small code, okay, and then we can also complete the exercises that we touched the last few days. So let me just go back to the. Okay, here is the code. Now this guy will try to set. Okay. Okay, so this is the repo. Do a git pull just to find out the last modification. I added last night this MPI 101, where there is a small README file here. And here what we can try to do is actually to play with an MPI program, a very small MPI program. Simple enough. It can compute just the, by means of Monte Carlo, it estimates the value of pi. Well, you can read the way you do it. You just, you just throw a stone into a square, and then you count the number of stones that ends into instead of the square on the circle, and then you do the ratio between the number of stone threads and the number of within the circle, and if you have n large enough, you got to pi. We are working just in the first part of the axis, and so in the first part of the xy domain. Let's try to. This is actually the idea. Okay, we have a square. Okay, we have this, and when we start putting numbers, okay, random numbers. This is one, and this is one. And then we have this, and the number. The ratio between the total number of points within this stuff, it is actually a quarter pi. Okay? So this is a very simple algorithm. This is a Monte Carlo algorithm. So we just wrote in a serial way, and then we also parallelize it. And then we ask you to do some operation on this. So the first is actually just to familiarize with the code, the serial version and the parallel version. So are you on the cluster? Did you find the source directory? Okay, so pi is actually the parallel, the serial version. Okay, and less MPI underscore pi is the parallel version. We will see when we will comment in a moment about that. First of all, let me choose a few resources where to run on. So qsub, I should have a qsub here in my history. No, it's a qstat, this one. Okay, so I'm asking a full node, 72 cores, okay? And then I'm here. And what I can do is actually simply try to, I choose a compiler. Well, yeah, I choose module load GCC. Let's use GCC 91. Then module load OpenMPI. Okay. So now I have a compiler, GCC -v. Ah no, because I have to say GCC 90, no? Okay, so here I have GCC 91, 99.1. Okay, I can compile the Pi code, and then I can run the Pi code, and it tells me that it wants the number of iteration, that is the number of iteration I try to compute. So if I do something like 10, actually the estimate of pi is quite poor. If I do 10,000, I start reassembling pi, but I need a certain number of move to get a decent approximation. 3.141 is good. Let's go a little bit further. And here we see this. Of course, you see that increasing the number of iteration, it takes more time, of course, that's correct. And the time is actually spent mainly in generating a random number. Okay, so if you profile this code, you will see that it's actually just the time takes mainly in the random number. Perfect. So this is the parallel, the serial version. We can also time it, user bin time. Okay, and let's take this just to have enough time to run. And so we have a reference. We have a serial algorithm as reference, and this is actually our reference to compute then the parallel scalability of the other program. Okay, 16 seconds. Okay, this is a very good program. You see, we don't have any. You see here, 0 system time. It doesn't do anything in system time. That's correct. So 99% of CPU, 16 seconds to compute how many? 1 billion, correct? 1 billion movements. So 1 billion movement in 16 seconds. So the code is really simple. We are okay with that. Now let's take a look at the parallel implementation of it. Okay. Well, this is actually standard things. Okay, here I have defined the integer my int, number of processor and processor. Okay, my rank and size in the slides that I show you before. I define double pi as 0. Then I have a master process, and for this master process I define also a tag 1, 2, 3. Okay. Then I initialize MPI, remember, MPI init, MPI common size. MPI common size returns the number of processor. And then MPI common rank return the rank of my processor. Okay? And then it says, okay, then we say if argument is less than 1, you have to play with this command this way. Okay. Then what we do? Well, we read the integer as a long because we want to have a very long integers, okay? And we have that the number that we read is actually divided by the number of processor. Okay, so it means that if we have 1 billion and we have 8 processor, we will assign 1/8 of this billion, that is actually 125 millions of move on each processor. Okay, the idea is this, we will parallelize it this way. Okay, then I take also a time, MPI wait time is actually, wall time is actually a routine that starts a clock. Okay, then here I initialize my random numbers, and then for I equals 0, I less than n, I generate 2 random numbers. I check if these 2 random numbers is within the cycle, so thank you, and then I increase the local counter, local n++. So this is actually more or less the algorithm, and then I say if I am processor 0, the master, I'm gathering results from other, and I'm doing this in a very stupid way, the trivial way, simple way, in which I say, okay, m is equal local m, and then I do for proc equal 1, proc less than number of proc, okay, MPI receive. So there is a loop that this guy say, okay, I should receive by all the other processes. I receive what? I receive local m, that is actually one element of an MPI long that should come from proc in the loop with a certain tag, okay, with MPI and then MPI common word, and then I have the status of the call of the receiver call. Once I receive that, I sum up m, the local m, I sum up, and then finally I compute m. I compute pi as 4 because I'm just a quarter of the cycle. 4 times m, local movement within the cycle, multiplied by n times n proc, because it's the total number of procs. Is it clear what is happening? So you see, the communication here is simply that. Let's start all together. Compute n. Have n to compute. Okay, they start doing this. Then when processor 0 completed their its operation, it does a loop and wait for each of the processors to receive the local sum computed by each of the processor. Is it correct? Is it clear? And then I take also the time. And then I say, okay, within my ID, I also say print the number of trials, the estimate of pi, and then the wall time on the master node. Remember that I have n processes, and here I'm taking just the wall time on the master node. Okay? Of course, if I'm not processor 0, what I have to do is actually to send something. And I send local m, that is one number of kind MPI long to the master with tag and to MPI communication word. Okay, so here the situation is actually if I'm not master, I'm doing my calculation and then I send the message. I'm sending in a blocking way. Okay, so what does it does of this guy here? If for instance, if I am number 5, okay, and I completed my calculation, when do I send? When I do return from this MPI send, I will return only when this loop have proc equal 5. So in this way here I'm serializing, I'm serializing the collection. That is really, not really so well done, no? Because I'm saying, okay, I'm receiving, and I'm not saying I receive from the first. I'm receiving from number 1. And if number 1 is the last one, all the other are waiting for them. Then I receive from number 1, and then I'm ready to match the call from number 2, and so on and so forth. Okay? So not really an appropriate way to do things.
So it's not the first that that's finished.
Send the data and close. First that that's finished, just stand there waiting for the other coming. And if number 1 is the first to complete, okay. But if number 1 is actually, if number 1 is the last to complete, all the other are waiting for him.
But with the result ready, right?
Yeah, with the result ready.
So is this relevant in some context? I mean, I think that it is a little bit compared to the time of computation, like the collection time.
Yeah, it could be a little, it could be, but I mean, that's actually another interesting part. We would like to measure how much does it take the communication operation and see if there is any other way to do a better communication pattern, okay? In any case, this is actually the program, so you can try to run it. So I can compile. Remember, compiling an MPI code means that we need to have a wrapper. Let's look for the wrapper. We have it. This is MPI CC, so we can do MPI CC. Pi MPI, no, MPI minus O MPI pi.x. Okay, and then I can run it. You remember, to run it, I can do an MPI run minus MP 5, for instance, MPI run pi 1 billion. 1, 3, 1, 3, 1, 3. So, here are the results. Number for trials, 1 billion, hopefully. Estimate of pi, 3.14, 166. Whole time on master process, 3.38. Are you happy with this? How many cores? 5. Let's do on 1. Okay, so running on 5, okay, takes something like 3.38. So if I multiply 3.38 by 5, I got something like a little bit more than 16. Not too much, but something like 17 probably. Let me just do it on with my powerful computer. So if I do 3 point, ok, bravo, l'hai fatto veramente? Sì, 13.9, ottimo. Ok, so, are you happy with that? Remember scalability, linear scalability and whatever? So, here I have 5 cores, okay, and it takes 3.38. Scalability is defined like the time it takes on one processor divided by the time it takes on P processor. It's a function of P, okay? So here I have that my scalability is actually 16.38 divided by 3.38. That is not far from 5. Okay, this is something like 4.1. So it means that I'm actually efficiently using my cores. Okay, so increasing the number of cores, I'm actually decreasing almost linearly the time it takes to go to solution. Okay, so this means that my scalability curve here is actually one processor. Okay, here actually n processor. My 0.5 here, okay, is actually given by this number divided by that one. So let me just do it, just to be sure. 16.37 divided by 3.38. So 48.84. So this is 5. You are actually a little bit less time. Okay? So quite good scalability. Let's now increase the number of cores.
And I expect that for low numbers, compared with 1 million, and compared with the available cores, this should go straight.
Yeah, let's try with 2. $833. So this means that I have to do 16 divided by 833. 9.7. Then you can go. So it looks like that. Yeah, these 2. Okay, you are actually doing well. I Are we doing well also for for higher number? What do you think? Well, at a certain point, no, because actually the time it takes to compute will actually decreases, okay, in favor of the time it takes to communicate the results. And this can be done, for instance, let's try to see, no? If things are working perfectly linearly, I should see that if I run on 72 cores, it would take less than 1 second, because it will be, no, well, 1/3 of a second, so it's 1672, no, 1/3, 1/5, 0.20, something like that, no? Should we see this number? Well, not bad, 0.31. It scales perfectly.
Yes. Good problem for MPI.
It's a trivial problem for MPI, of course, but I am a little bit surprised how well it scales this guy. Let me see. Because I mean, 0.31, what is 0.31? Where's my 52. Not so good, but it comes out that out of 72 cores I'm running, I'm using 52 of them efficiently. Okay, and in fact we can define the efficiency as actually the scalability divided by the number of cores, and so we have that if 52 divided by 72, that is actually in the order of something like 0.8, something like that. So these are actually quite good numbers. I mean, having a code that scales with the efficiency of 0.8, it's not really bad. Okay.
I mean, this is of a very small problem size, sort of like the scalability is. I've seen it, for example, to not be constant. If you increase the problem size, like for 10 atoms, it scales very nicely. Then if you have 100 atoms, it scales sometimes better for some systems. For again, when I've tried it with molecular dynamics, then you very quickly see a saturation in the scaling with the size. So how does the problem size figure into this?
That's a very good question. The problem size is actually quite important. Let's try to do that. So what do we expect? I mean, now I have 1 billion. If I do less than 1 billion, let's say that we do 100 million. I take away
It keeps the same amount of scalability.
by the way, why I have this number? Number of trials is not actually equal.
You can divide by 72 the integer.
Yeah, correct. The integer is not allowed, so this is actually a bug. I mean, for computing pi, who cares? But if you have to compute something different, I mean, we are missing some elements here, okay? So if it is actually important, that's actually because we are not taking care correctly about the remainder of the divisions. Okay, so we do a very stupid division, okay, and so we just this code should be written runs only for a number of cores that is an exact multiple of the number of moves, an exact divisor of the number of moves. Okay. Well, let's forget about it. This actually runs very well, but if I run this on 1, so it's 0.04, here is actually 1.82. So it looks like that the factor is actually just 5. So I'm wasting a lot of resources here because actually my code doesn't scale because actually data size is too small. And what is happening is actually that the computation is done in a very simple way, very rapidly, but then I have to communicate. And now the quantity of the communication time is getting larger and larger and is actually closing down my scalability under load. Okay, so the fraction part, okay, the serial fraction part, in this case is the communication part, and actually yesterday Luca discussed this in details, is actually flattening your scalability curve. So generally what is happening is actually that under load is quite good actually to give you a clear view of what's happening, but generally you have to think that your problem when you need course should be large enough to do something on the course. This problem here, with this number of trials, is not large enough. Okay, that's why. And generally what you see is actually that, for instance, in molecular dynamics, you see that if you have a small problem, it doesn't scale well. When you have a large problem, it scales perfectly. It takes ages to be completed, but actually it scales perfectly. Just because, I mean, it's actually just crunching numbers, and communication is completely negligible. And the same also for quantum expression, for all other codes. Okay, so if you have a lot of computation to be done, okay, that's actually, you can think to scale well. The point here is actually that sometimes there is this trivial code, just because it's important, it is actually nice, it's a Monte Carlo code. Monte Carlo, you know that everybody here in this room, I suppose that Monte Carlo means no communication at all. That's correct, no? Because we can compute a portion of our problem, and then we just need to send out a number. Okay. In molecular dynamics, okay, it's not this way. Every single step you have to communicate with other atoms, where you are, which kind of forces you have, and so on. This is a case of molecular dynamics that is actually quite well scalable in part, because I mean I saw wonderful scalability graph for very large system of molecular dynamics. Quantum espresso doesn't scale this way, because it's much more complex. There is much more communication between processes while the communication goes on. On bioinformatics stuff, probably you are in the right way, in the right place, because you don't, I mean, as far as I know, there are a lot of problems that are actually completely separable and embarrassingly parallel. That's actually the question. This is actually an embarrassingly parallel problem. That doesn't mean that it's not easy to parallelize it, but it means that the communication, that the problem can be split easily, okay, in independent worker, and then I have just to collect a few numbers and not too many. Monte Carlo, analysis and so on with parameters of this kind. Other codes are much more complex. Yep.
Before you said that you were surprised by how well it scaled with 1 billion when you reached the 72 cores.
Yeah.
Now I am surprised at how bad it is emerging the problem about the communication time compared with the calculus time. Here, when you
decrease the size
to
10 million. No, this is actually what all the billion. So it's 10 times less.
Yes, and I think this is related with the fact that it is very fast in doing each processor that 100 billion divided by 72. And here the communication, which is not marginal, it is fixed time. It is comparable with the start to be comparable with the time it takes to perform all the loop each process, right?
Correct, exactly.
Instead, when you
exactly this.
put a larger number,
They are just computing, and then the fraction of communication is actually negligible with respect to the fraction of computation. Okay, and the fraction of computation is perfectly parallel under law, while the fraction of communication is not at all parallel because it actually involves all the processes. So it's a serial part, and so this is actually decreasing your scalability. And so you will see, and this is actually one of the exercises that I ask my student to do, is actually just plot the scalability. I mean, it's also written in the test. I don't know if you want to try whatever, but you see that if the size is large enough, you go quite well. Okay, but if the size is small, you will easily do this way. Okay, and then you can also compute the overhead of communication. Okay, and remember that you can make some numbers, rule of thumbs. When we decrease the number of computation by a factor of 10, so from 1 billion, 10 to the 9th to 10 to the 8th, okay, I'm decreasing on each core, on each process, by a factor of 10 the number of operation, correct? So, but I keep constant the communication. That's actually the point. so I'm decreasing the computation, so the computation goes down by a factor of 10, okay, but communication is always the same, because I always have to communicate a long guy, a long integer to all. So, there is another important point here that was mentioned by Luca yesterday, and we can try to do this. That is actually trying to do a weak scalability approach. Okay? Remember, Amdahl law refers to strong scalability. I have a problem of fixed size, and I want to decrease the execution time. That is perfectly fine. Sometimes it's the other way around. I have a problem, okay, and due to the fact that I have a larger computer, I don't want to run a problem of this size. I want to run a problem of much larger size. And so I will actually try to compute the weak scalability, because I will say, I have a problem that on one machine, one node takes X time. Okay? Now I double the size of the problem. How many machines do I need to keep the time constant? Okay? So this is actually the Gustafsson law, and it is actually what we call the weak scalability. So generally what you want to do is actually to do plot of weak scalability. So the idea is actually to say, okay, I run this guy, okay, and when I increase the number of cores, I increase also the size of the problem I'm computing. So for instance, this means that if the code scales well from the point of view of weak scalability, when I do this, MPI run minus MP, let's say, this is actually 10 or, well, let's see. Okay, so this is actually 1.6. I would like to do this. Okay, now what I'm doing, I'm actually doing a run on 8 cores, but now the data set I'm working on is actually 8 times larger. And I'm thinking and I'm hoping that the time remains constant. If this is true, it means that the weak scalability is good. And so my code, I can actually increase the size of the code at a reasonable time. That again is not bad, because you see, it completes 8 millions, 8 millions, 800 millions of move, okay, in 1.678, whatever, and before 100 was actually 1.82. So it is even better. This is actually probably due to the fluctuation. So if you just present me a relation with just a report with just one number, I actually reject the report, okay? Because I mean, these actually experiments, and so you have to perform the experiment at least 3-4 times to see what is the fluctuation around. So let's do it again. But in any case, this tells you that the code 1.74, yeah, is stable around 1.7, okay? And then we can go for 64, okay, and go this way. Okay, so I'm doing now 6.4 billions in total. Is it correct? No. No, faccio uno zero. Eh? Now I have 64 of them working well. You see, now the time actually increases a little bit. But now I'm doing a very large number of moves, okay, this way. So there are different things, okay? So just to come back to your question about scalability, I mean, I don't know which kind of science you're doing, but generally what you think, I suppose that you have your system and you run some simulation. So the first thing to do for you is that you have a fixed system size, and so you have to do a strong scalability test, no? Just to see which is the appropriate number to run your problem. But then if you are, for instance, if you have a different approach, like my friend over there, Luca runs galaxy simulation and whatever. So when I give him a very large system, he won't run the small system that it runs on a small cluster. It will actually enlarge the system to run a much better simulation. That's the point. And maybe also for you.
Yes.
At a certain point you can say, your boss can tell you, well, 10 10 molecules doesn't tell us anything from the scientific point of view. Please scale to 100.
Also, we use periodic boundary conditions,
Exactly.
so we use a bigger chunk.
A bigger chunk, and so you have to enlarge your system, and you have to have more resources to do that. And this is in any case you have to do a little bit of weak scalability test just to see where you are. Okay. Yeah, that's actually more or less the situation. So this, I mean, here I'm proposing a small exercise. There is another important point that I would like to tell you. This is the following: that I run this, and then I run this, and I run a parallel program on one processor. That is not actually correct from the point of view of computing scalability. Because scalability should always be computed, because remember, scalability is defined like the speed up of scalability is defined like the time it takes on one processor and the time it takes on P processor. But the time it takes on one processor is not actually the time it takes the parallel approach on the one processor. It's actually, you should always consider the best algorithm, serial algorithm that solve your problem. And so in this case, probably there won't be too much difference, but we should actually compare these numbers, not just with this command, but with this command. Let me see, I have no n8.out. A.out, and this actually, this is actually a very small number. Yeah, in this case, the two algorithms, the parallel implementation and the serial one are quite similar. I mean, of course, there is a little bit of overhead in the parallel one because you call the MPI routines and whatever, but on a very small program like this one, it's probably negligible. But on other examples, it could be really different. Okay, and sometimes a vendor cheats on this. Because they tell you, look, my scalability is perfect. On my system, your program will scale perfectly. But it's actually they consider the parallel program also on one processor. And the parallel program and the serial version can be quite different on a complex code. Okay, because there is a lot of overhead caused by the fact that you introduce an MPI, you introduce a lot of different variables. Maybe the footprint in memory is different because you need additional arrays, additional data structure to accommodate then your parallel approach, and this actually can cause a much larger computing time. So sometimes you have to be careful about that. Okay, so what I would like to propose you is actually in the exercise. What I was telling you is actually, let me just go back here. There is a README. Okay, so we familiarize with the idea. Sorry, here the cluster is actually based on our cluster, and that's why actually I was surprised about the good numbers that you have, because for our cluster that is a little bit older, scalability is not so good. Okay, so because the CPU is lower. Here we see that with respect to our cluster has CPU that are lower than the one here, and also have a network that is lower. Okay, so here we have high CPU with a high network, and so it's actually a very good situation, and so scalability is very good. So here is actually the way you can run. We already understood that. Remember that we split the number of trials, so if we say a number here, this is split, okay? And then you can analyze the parallel solution and improve it. Analyze the parallel solution, improve it means that we are not very much satisfied with this very naive way to communicate between processor. We can actually replace this loop with another approach. What can we use, for instance?
MPI
An MPI reduce. Exactly. MPI reduce. So I suggest you, if you want to try now, to implement this code using MPI reduce. That is quite trivial. If you don't like to do by yourself and you are too lazy to do that, there is also the solution provided. Okay, so I mean, so So the point is actually that when we do an MPI reduce here, what we are doing, that all the processor now call MPI reduce, okay? The buffering, the first element will be the local sum, the second element will be the global sum. We will have again one element, okay, and one element of MPI long. And if we call MPI reduce, we just say 0 because we are on the master node, and then status and tag and whatever. No, status and no more than status. Try to do it. I mean, I will. Can you do it? No, because you don't have the slides. But I can put the slide over there, and then you can see which is the way to do this. Let me just see this. Reduction. Yeah, this is actually the stuff. So, this is actually Fortran, sorry. Do I have the version for MPI? No, I don't have the version. Let's see version. Okay. This is, so we have a send buffer that will contain the local sum, okay? The receiving buffer that will contain the global sum, that will be automatically computing within this reduce operation. The int count, that will be 1. The MPI data type, that will be MPI long, whatever. The MPI operation, that is a sum, in this case, MPI sum. And then the integer root, that is actually master. Here we have to place master instead of root, and then MPI communication. So you can try to modify it. So what is actually happening is actually that this no, it doesn't have anything to do. Okay, instead of writing my ID 0 or whatever, okay, you can actually write here, okay, implement here the MPI reduce. Okay, and then you will just leave, instead of leaving this, the code will be MPI ID 0, pi is this, because now M comes from the stuff, so you have to comment out this stuff here. This is no longer needed because M is computed by the MPI reduce operation. Okay, so if my ID is 0, you just say pi, you compute pi, because now we have to do this operation. Well, all the processor can do this operation. Compute the time and then print out this kind of stuff. Okay, well, so this, and this actually is no longer needed, okay, because everything goes here. I have to place an MPI reduce here. Okay, I mean, this is actually my suggestion. If you are in trouble or whatever, there is the solution, and you can check the solution. It's 10 minutes to 12. Maybe you can play with it, and then at the beginning, after lunch, I can comment on the solution and go on. While you are doing this exercise, I'm actually would like to point out other stuff here for the sources. From this exercise. So you can analyze the parallel solution and improve it, and then check if there is any advantages in doing this operation. Probably you won't measure it too much. Okay? And then you can try to run some strong scalability test, that things that we tried, and also you can run some weak scalability tests that we tried and formalize it. I mean, this actually generally is an exercise that I propose to my student. They take a couple of hours to complete and do the graph and whatever. Of course, you don't have the time to do that, but I mean, he's here and we just scratch the surface and grab a little bit the feeling of how the exercise can be done. I think that in few minutes you can try to do this MPI stuff if you want. Okay, and then we can go for lunch, and in the afternoon what I would like to do is actually that we can start doing, well, there is the OpenMP 101 exercise that look if you want, but otherwise I would like to go on with the multi-core, multi-CPU, multi-core exercise, playing with MPI, okay, and trying to benchmarking the performance of your MPI class, to measure the performance of MPI on your cluster, within the node, within the socket, within and across the node, just to give you a feeling of how latency and bandwidth change across this. Okay, and then we have also again stream, and what else here? Then I have AVX. AVX yesterday did I show you AVX very rapidly? So we can show also, we can take a look at AVX, and then I would like to do this exercise on GEM together. That again is trivial. That is actually the usage of matrix multiplication on CPU and on GPU, and try to see which are the differences and discuss a little bit about that. Okay. And I think that we have enough time for the afternoon. Okay, did you succeed in putting in your MPI reduce? Are you working hard, or are you just taking the solution? No problem for me, actually. vedere la performance, non è... No. No, no, è solo per vedere che giri. IB maiuscolo?
IB maiuscolo, net underscore time.
È andato sullo stesso.
Infatti, guarda, la risolvo voi in un altro modo.
Vabbè, bene questo, così facciamo vedere anche i diversi...
Scrivo con una coda in email così.
Are you succeeding doing this exercise? Still working?